Okay, number one, there's kind of two approaches to this. The first would be just to rewrite tangent squared as sine squared over cosine squared. So number one. So first possible approach. Cosine squared x times sine squared x over cosine squared x. And then 1, and you just have sine squared. And how do we do sine squared? Half angle formula. Half angle formula. That's the most important integral of this whole section. Okay? Knowing how to just do cosine squared or sine squared, use the half angle formula. So it's going to be 1/2 minus 1/2 cosine 2x. If you want to factor out the 1/2, that's fine. I just distribute it. So that's 1/2 x minus 1/4 sine 2x plus c. That's one way to do it. Questions on this approach to that problem? Okay, the other way is you could say tangent squared is secant squared minus a question. Oh, no. You could say that tangent squared is secant squared minus 1. Okay, and then distribute the cosine squared. And cosine squared times secant squared, well, that's just 1, because secant squared is 1 over cosine squared. And then cosine squared times negative 1, 1 minus cosine squared. From here, you could just write it as sine squared. That's equal to sine squared. Or you could do this integral, which would be x, or sorry. So then we need half angle, 1 minus 1/2, 1 plus cosine 2x. And then you're doing the same thing. So it'd be x minus 1/2 x minus 1/2 sine 2x plus c. Okay, so two possibilities. Questions on not grading, but the problems, the solutions. Does it make sense? Yeah, yes, sir.
Where it says 1/2 minus 1/2 cosine 2x,
yeah.
Why did you replace the 1 with the 1/2 and put 1/2 in front of cosine?
Yeah, if you factor the 1/2 out, you're saying?
No, I'm confused why you put 1/2 in there instead of the 1.
So sine squared is 1/2 times 1 minus cosine 2x. So just distributed the 1/2. Yeah. Other questions about either of these approaches? So they both boil down to sine squared or cosine squared, whatever you take the pick. Okay, that was the point of problem 1. Was to use an identity and then you get either sine squared or cosine squared. Okay, so we'll do that out of 10 points. So if you got it to either sine squared or 1 minus cosine squared, that's basically half the battle, so 5 points, and then solving it correctly from there, that's the other 5 points. Use your best judgment, okay? We can't use your best judgment. So 5 points if you got it to sine squared or 1 minus cosine squared that way, and then the second 5 points would be for finishing the antiderivative correctly. Use your best judgment. Other questions on number 1? Okay, I'm going to erase everything. Number 2. So sine 2x is 2 sine x cosine x. And what did I have? It times what? Another cosine? So here's this one. So basically we have 2 sine x cosine squared. And immediately we recognize, what do we have? Undoing, which one? Chain rule, because sine is essentially the derivative of cosine. So this is our g prime f, and this is our f prime.
So we're going to just do the antiderivative of something squared, which is something cubed, or 1/3 times that thing cubed. And then we got a mess here, so we got the 2. And then when we take the derivative of cosine, we actually get negative sign. So we're going to need a negative sign. So we get negative 2/3 cosine cubed plus c.
Okay, 5 points for getting this far. 2 sine x cosine squared x. 5 points for the rest. Doing that correctly. Questions on the solution? Use your best for grading, use your best judgment. But any questions on the solution to this? Does it make sense?
Last one. Cosecant to the 4th, cotangent to the 7th. Is that what we had? Okay.
So the key here is that what is the derivative of cotangent? The derivative of cotangent is
Negative cosecant squared. That's the key to this. And so, and we saw that in yesterday's example and the ones you had in the homework. So what we would really like to have is an isolated, if we get an isolated cosecant squared and then everything else with cotangents, then we can undo the chain rule, right? So I'm going to isolate a cosecant squared. And that leaves me with another cosecant squared. And still the cotangent to the 7th. Again, so the key to this is, what's the derivative of cotangent? Cosecant squared. So I'm gonna isolate a cosecant squared, knowing that that's going to be like my f prime, right? And I'm doing the chain rule. That's going to be my f prime.
And if I can get the rest of it all in terms of cotangent, then I've created the situation where I can undo the chain rule. G prime f, right?
Okay, so I need to switch this into cotangent. How do I do that? Yep, this will be 1 plus cotangent squared. And so then I can distribute this stuff out, and I get cosecant squared x times cotangent to the 7th plus cosecant squared x times cotangent to the 9th. And so then I can do, so now look, I've got cotangent to the 7th, and then that's our g prime f. F being cotangent, so f prime is cosecant squared, or the opposite of. Same thing over here. So it's going to be 1/8 cotangent x to the 8th. But then I'll need a negative, right? Because the derivative of cotangent is negative cosecant, which we don't have a negative, so we need a negative. And then similarly, it'd be minus, what, 1/10 cotangent to the 10th.
Questions on the solution? We'll talk about grading in a second, but again, the reason that we grade it together is for the learning, for the making up for where your deficits are, for coming to understanding. So, questions on the solution? How many, just I'm curious, how many people were mostly successful on this problem? Mostly successful. Not very many, okay? So, it should, okay, so that this is, it's similar, we have an example in class, and then you had some on the Weber, maybe one of the Weber didn't go well, but, so this pattern, looking to create undoing the chain rule by isolating what, the f prime. That's what we're doing with this. Okay, so, just say, if you got this far, you isolated cosecant squared, 3 points. If you got this far and you were ready to take antiderivative, 3 more points. And then the rest, 3 points, and then give yourself 1 point for free on number 3. So 3, 3, 3.
Can we infer from this problem that we're going to have a sum of 2 terms because we have like 2 cosecant squares? Like if it was cosecant to the 6th and some other.
Yeah, so if it's cosecant to the 6th, we're gonna have a cosecant to the 4th, and this is gonna be a square binomial, so it'll be a cube, you'll have 3 terms, right? Because it'd be cosecant squared, so it'd be this thing squared, then you get 3 terms. But they still all just be in all cotangent, so you can still do it.
Right.
Just be a little bigger.
But if it weren't cosecant to the 6th, we would have 3 terms in our integral at the end.
Yeah, because this will have 3, right? So this, it would be this thing squared, and when you square a binomial, you get 3 terms. Okay, so there were 30 possible points. So what's your score? So whatever your total was out of 20. Yeah. This one? I just distributed this all out, right? So cosecant squared times cotangent to the 7. Cosecant squared times cotangent to the 9. Just distributing, just multiplying it all out.
It's a total out of 20.
So you're going to add up all your points and then put it out of 20. Yeah.
Okay, here's my notebook for giving me lines. All right, so the next technique is called partial fractions. So partial fraction
Decomposition integrals.
Okay. So if we have an integral like this, first thing we ask is what? What's the first thing we ask? Undoing chain rule. Is it undoing chain rule? Yes or no? No. How could you make a change to the denominator so that it would be undoing chain rule? Everyone thinks themselves. Everyone should be able to do this. What change would you make to the denominator so that this was undoing chain rule? Everybody should be able to answer this question. Travis, what do you think? What would you need in the denominator for this to be undoing chain rule? Not sure. Is it tie? Tie? Yeah. What would you need in the denominator for undoing chain rule? What power? What power? Yeah. Only one power works. There's only one power that works. What would it be? Power 4. Matthew.
I was going to say you change the denominator to so that it would multiply as like 2x to the 3rd times x plus 1 to the -1.
Okay, so how are you going to change the denominator? She's suggesting that we change that x to x to the 4th.
Sounds good.
Joel?
Would it be better if it was to the 7th?
X to the 7th?
No, the second.
X squared.
That's what.
Okay, so are we changing it? Sorry, I thought you said something. So x squared plus 1 or x to the 4th plus 1? Brandon?
Thinking maybe 1 x to the 0.
Well, so of course that would work, but then it wouldn't be undoing a chain rule. You just have 2x cubed, right?
Yeah.
So we want something else. Yeah, that's a trivial case, but it's true. You're right.
Why don't you just say x to the 2 plus 1?
All right, so we got x to the 4th, and we got some votes for x squared. Gino, what do you think?
to the fourth. Michael, what do you think? X squared. We're a divided country here. Divided kingdom. Yeah. What do you think?
I wrote X squared, but
What X squared? X to the fourth.
What was that?
Last vote, Karen.
Square.
X squared. It's X to the fourth. It's X to the fourth. Why? Because we'd have 2x cubed times x to the something plus 1, what, to the negative 1. So where is your g prime f? Is this your g prime f? Or is the second your g prime f? This is your g prime f. So therefore this is your f prime. So therefore that needs to be 4. Needs to be 4. Then you would be natural log of x squared plus 1. And then whatever factor mess you have to clean up, right? Okay, but we don't have that, right? We have 2x cubed over x plus 1. So we might try undoing product. Okay, but I want to show you something else. So the first thing with this is so it's a sort of a rational functions. Rational function is one polynomial divided by another, and that's what we're looking at. One polynomial divided by another polynomial. First thing is if the degree of numerator is greater than, actually, or equal to denominator, yeah, then long divide first. So we're going to long divide this.
You had to do that.
Yeah, we're going to do this. Okay. And so long divide means that then either you'll have something that you can do, you'll be done, or you can continue on to the partial fractions decomposition, which is, we haven't done that yet. Okay, so this is kind of a initial step that you would do before the method that we're about to learn. Okay, but this may take care of it. This may just, you may get to a point where you don't need to do this. So we'll do it here. So we're going to long divide. So that means we're going to let x plus 1 we're going to see how much that goes into 2x cubed, which is 2x cubed plus 0x squared plus 0x plus 0. Okay, so then so when you long divide, you want to have 2x cubed minus 2x cubed equals 0. So what do we need to multiply by x to get positive 2x cubed?
What did you just say?
You remember long division? You don't?
No, not at all.
Okay. Well, when you long divide, we're gonna multiply by something so that when you subtract, the 2x cubed goes away.
So we're changing the denominator.
Nope. Yeah, so maybe if you've never done long division before, then we probably need to do it outside of class.
Okay.
Yeah, because it's going to take too long to teach it from scratch. But so we're going to be subtracting, right? And our goal is we need to get a minus 2x cubed, right? So what do we need to multiply x by to get a plus 2x cubed? 2x squared, right? We're going to have 2x squared here above x squared. So 2x squared times our x is the 2x cubed. And then 2x squared times 1 is 2x squared. Okay, and then we're going to subtract. And when we subtract, what do we get? Negative 2x squared. And then we bring down to 0x, right? And then we ask, what do we need to multiply x by to get negative 2x squared? Negative 2x. Okay, and then we're going to get, we're going to subtract, right? And we're going to get plus 2x. We're going to bring down the 0. And we're going to say, what do we need? Plus 2. So we get 2x plus 1. And we subtract. Plus 2. Just kidding. Right? So, and then we're going to subtract. And we're going to get negative 2. So then 2x cubed over x plus 1 equals this, 2x squared minus 2x plus 2. What? And then here's your remainder. You put your remainder over your divisor as your last term, so minus 2 over x plus 1. So this now is doable, right? We don't need to learn anything new to do this. So that's equal to that. So that original problem then essentially equals, or it does equal, not essentially, it does equal this. And we're all free, piece of cake. Okay, so that has nothing to do with partial fraction decomposition, though. Okay, but we want to do this first. So what happens is, then you may get this last term may be another rational function that requires this, that we're about to do. But sometimes the long division just takes care of it, and you're home free, and you can get the antiderivative with nothing new that we haven't learned. Okay, but, so this last term may or may not require I'll call it PFD. Hopefully there's not something controversial with those letters. Or offensive. Not that I know. Okay? But I mean partial fraction decomposition. Okay? PFD. So in this case it does not require that, and we can just do it. Okay, so and that would be, if the degree of n is greater than or equal to d, you're going to start by long dividing. Okay, and then notice now the degree of d is greater than the degree of the numerator. So we wouldn't long divide again. Okay. Questions on this so far?
You said partial fraction differentiate. Decomposition.
Wait, what did you say about the power too?
Well, now notice that this now is d is greater than n. So you would never long divide again. This is never going to put you in the situation where you would long divide again. You could just either you can do it like this one, or you were going to use the partial fractions. Okay, so our first step was if okay, second step. Okay, so another example. (5x plus 1) over 2x squared minus x minus 1. Okay, so second step is if d can be written as a product of factors, the denominator can be written as a product of factors, then you're going to decompose this function into the sum of partial fractions. So basically, if that denominator is the product, a multiplication of several factors, then we can write it as the sum of fractions such that that denominator we started with was the common denominator. Right? Because that's what a common denominator is made up of. It's made up of the product of the original denominators, right? So, do we have that here? Can d be written as the product of factors? Meaning, can you factor that? So, 2x and x. And then this would have to be plus 1 and minus 1 in order to give a sum in the middle of negative 1. Does it work? Can we do it? So I need a minus 1 and a plus 1 so that when I do those middle terms, I get negative x. Plus 1, x minus 1. That does it. You get 2x squared, you get a plus x and a minus 2x. It gives you the minus x, and then plus 1 times minus 1 is minus 1. So basically, this fraction then, we think of this as the result of adding fractions, and that we've got this common denominator, right? So it's kind of like adding fractions but going backwards and decomposing them. Okay, so we want to write 5x plus 1 over 2x plus 1 as something over 2x plus 1 and something over x minus 1. And that's not cross multiplication. That's when two things are equal. You're undoing adding the fractions. You're undoing adding the fractions.
See, one just the numerator times the first factor, and the second one is the numerator times the second factor.
Let me just go a little further and see if it answers your question. Okay. All right. So basically, then, to get a general form of what's going to be up here, it's going to be 1 degree less than what you have in the denominator. Okay. So a general form. So we don't know what's up here. We don't know what's up here. So we're going to put something general and solve for it. So what you put up there is going to be degree 1 less than what's in your denominator. So what's the degree of 2x plus 1? What degree is that? 1. So 1 degree less than that is? 0. Which amounts to what? A constant, right? A constant. So we'll call it capital A. It's just a constant. Because that's degree 0. And then we're going to have, what's the degree of this?
1.
Also 1. Degree of the numerator is also 0. But it's not going to be the same constant. It's going to be a different constant. So we're going to call it B. Don't call it A, because then you're forcing them to be the same when they might not be the same. So now we've got to figure out what A and B are. If we can figure out what those two constants are, then we got easy integral, right? It'll just be natural log. Both of them will just be natural log. Right? So how do we do that? Well, so now it's like we're starting here. We're going to add these fractions. What do we do? So we got our common denominator. So what would it be? So we're going to kind of, it's like we're decomposing it and then going backwards to figure out what those constants are. Right, we need to multiply the top and bottom by x minus 1, right? To add these fractions. So then this is going to be a times x minus 1. And then, so that we get the common denominator here, we're going to multiply top and bottom by. Everyone follow that step. Did I lose you? Does it make sense? Okay, so then what? So then this right here has to equal, this whole thing has to equal what?
Numerator on the left.
5x plus 1. So we need to find values of a and b such that this thing, this numerator over here equals 5x plus 1. So ax minus a plus 2bx plus b has to equal 5x plus 1. So what? We're going to gather our like terms together. We know that the coefficient of x has to be 5 and the constant has to be 1. So we're going to gather our like terms together. So what's our coefficient of x over here? What would our coefficient of x be on this side?
A minus 2b. Yeah. So what's
Do you see it? And what's our constant term on the left? Negative a plus b, or b minus a. Take your pick. So, again, we're looking for the sum of two fractions that equals our original fraction. That means constants. A constant over 2x plus 1 plus a constant over x minus 1. So we're going to add the fractions together, just keeping those constants as unknowns. All right, and then that numerator then has to be 5x plus 1. So what do we know about a and b? A plus 2b has to be what? 5. And negative a plus b has to be positive 1. Do you see it? So then solving two equations, two variables, there's a half a dozen ways to do it, but this one's all set up for us to just add the equations together. But any way you want to solve two equations, two variables, be my guest. I always just look for kind of the easiest way, okay? Which is different for different problems. But here we got a and negative a, so boom, let's just add these two equations together and the a's will go away. That's called elimination, right? Elimination. So 3b equals 6, b equals 2, and therefore a would be, so if b was 2, you can use either equation to solve for a, and a is 1. So you can, if you want to check that, you can plug your a and b in here and simplify that numerator, and it should equal to 5x plus 1. Plug in your b is 2, your a is 1. Do the math, you should get 5x plus 1. So. Okay, but so then essentially our initial integral then equals, do it in blue here. No room, shoot. I'll try anyway. Integral of, what is this, and then what does this integral equal? It equals? Why did we do all this work, right? So do you understand why we did all this work? We can rewrite this integral as 1 over 2x plus 1 plus 2 over x minus 1 which is now a piece of cake, right? They're just full of natural log. And then you're going to need a 1/2 on the first one, right? 1/2 natural log 2x plus 1, 2 natural log x minus 1 plus 8.
How did we know 3b equals 6?
I just added those two equations to eliminate a. Right? I've got a and negative a, it's all set up just to just add equations down vertically. Questions about this example? Okay, let's do another one. Can I erase?
Yes.
Oh, okay, and so then step 3. So I didn't leave myself room here. 1 is if n is greater than or equal to d, long divide. Number 2, then, if d can be written as a product of factors, which it could, in our case, then we can decompose the function to the sum of what's called partial fractions. Okay, then 3 is antiderivative of the new version of your problem. Antiderivative of decomposed sum. Antiderivative of each fraction, one at a time. That's the idea. I can't partially erase it like that. So if I erase this example, the steps go away too. Okay. Next one. Integral. Let's write this one over. Now, the degree of the denominator is greater than 3 to the numerator, right? What's the degree of the denominator?
X to the 3
It's cubed, right? Okay. And do we have product of factors? Yeah, it's already factored for us, right? So it's all set up. So this fraction right there can be written as something over x minus 3 plus something over now. So when we think about what is possible, what's the most general case for fractions that could be added together to give us this? Well, we need an x minus 2 to the power 1. But we could also have, what? An x minus 2 to the power 2 could be a possible denominator that would still qualify for that thing, that as its common denominator.
I don't understand that step.
We need all possible factors that could have this as the common denominator. So we could have x minus 3, we have x minus 2 by itself, or we could have an x minus 2 squared. All of these still have this common denominator. So we have to include every possibility. But, so then you ask, well, why don't we have x minus 3 times 1 x minus 2? Well, that's taken care of just by these added together. Does that make sense? So x minus 3 times x minus 2 would just be what you would get if you added these two together. Okay? So we need every power of every individual factor. So if this one's squared, we need it to the first and to the second. Okay, but it's this that's the key here for determining what's in the numerator, since that's still degree 1 there. It's just that our factor is squared, but it's the factor that determines what goes here. All right, so what will go here, a constant. What will go here, a constant. And what will go here? Still a constant, okay? So it's the underlying factor that determines that you subtract 1 from the degree to pick your general form. Okay, so now I'm going to go fast so we can get to another example, okay? But this gets a little more hairy because we got 3 things to solve for. So it's uglier. There's more algebra. Okay, so what's A going to be? A is going to be times?
Minus 2 to the 3rd.
To the what? So what do we need to multiply top and bottom to get our common denominator? Square, right? You see that, Brock? So to get the common denominator, all we need is we just need 2 of those, right? All right, and then plus B times what? Well, we're going to need an x minus 3 and then also an x minus 2. And then what do we need to multiply C by? Just x minus 3. Okay, did you count? And then that whole thing would be over the common denominator. our original denominator. And so this numerator then has to equal what? X squared, and then I'm going to put plus 0x plus 1. What do we got to do? We got to multiply everything out. We got to get like terms together. We got to get all x squareds together, get all our x's together, get all our 1's together, and that's going to give us equations for a, b, and c to find what a, b, and c are. Okay, so let's just, can we just look for the, can we just, and without doing that whole thing, can we kind of skip and figure this out? So what will our x squared be? So what will our, when we multiply that all out, what will our factor or coefficient of x squared be? A, we got an ax squared, is that the only one? And a bx squared, right? So would this be a plus b? Can you see it? If you need to multiply it all out and then gather your like terms, that's fine. But just for time's sake, we can kind of do this just by looking at it. Okay, and then what about our x? So x is going to be a little trickier to see, but we can do it. What will we have for x here? We're going to have minus 4x, right? We're going to have minus 4x, so that's going to give us a minus 4a here. And what will we have for x here? Minus 5x, minus 3x, minus 2x will give us a minus 5b. 1c. Did you catch it? So what are we doing? We're multiplying this whole thing out and gathering the x squareds, and then gathering the x's, and then gathering the constants, so that we find out what those coefficients are. We know what those coefficients need to be, right? We know they need to be 1 for x squared, 0 for x, and a constant of 1. Right, what about constant? So our constant term is going to be? What's our constant here? 4. So we're going to have 4a. What's our constant here? Positive 6. We're going to have 6b. And what's our constant here? Minus 3c. Again, equals that. Okay, so a plus b equals? No, a plus b is the coefficient of x squared. A plus b is the coefficient of x squared. So what does a plus b have to equal? 1. 1. The coefficient of x squared that we need is 1. Do you see it? What does this have to be? Minus 4a minus 5b plus c has to be? 0, the coefficient of x. And finally, our constant needs to be? Equals 1. Okay, so now do you somehow know how to solve for a, b, and c? So there's different strategies. Could you do it? Right? This is like advanced algebra or something like this that you've seen in a previous course. Can you solve for a, b, and c? So my strategy in this for 3 equations, 3 variables is to take 2 of the equations, eliminate one of the variables, and then combine that. So here we already have c eliminated, right? So we could combine these 2 second equations to eliminate c, and we have a new equation of a and b that we could combine with this one and solve for a and b. So what could we do here to eliminate c, in the second 2 equations to eliminate c? Yep. So we can multiply this equation times 3. because that would give me positive 3c, and when I add it to this, I'll get negative 3c. Then I'll have a new equation that just has a and b in it, and I can combine it with this one to solve for a and b. So negative 12a and 4a, negative 8a. Negative 15b and 6b, minus 9b. Positive 3c and negative 3c, 0, that's what we wanted. And then 3 times 0 plus 1, 1. Now I can combine these two. And once you have a and b, then you can use any of the other equations to solve. You can use the second equation then to solve for c. Plug in the a that you have, plug in the b that you have, and solve for c. This is just a lot of algebra, okay? Which you should, this is all prerequisite knowledge. So just a lot of algebra to do this. But don't lose sight of the goal. We're trying to figure out how to break apart this fraction into the sum of several fractions. So it's like we're adding fractions but going in reverse. So we need these expressions, or in this case constants, that will make that expression equal to that one. So if you keep that in mind, that will drive your method here, what you're doing. Instead of just memorizing, right? It shouldn't be memorizing. You should understand what we're doing. Okay, so I can start one more example. We'll just go to have this example on video. So you can confirm later that you get, here's what you get. A equals 10, B equals negative 9, and you can write this down and confirm it later. A equals 10, B equals negative 9, and C equals negative 5. Okay, and then that gives you 3 easy integrals, right? 10 over x plus 3, natural log. Negative 9 over x minus 2, natural log. 5 over x minus 2 squared, it's not natural log, but it's still really easy. It's really easy, okay? So that's just something to the negative 2. It's just power negative 2, which you can do, just undo the power rule, okay? Okay, let me start one more example, just so we see something different. I'm sorry? No. No time. Okay, so last one, 10 over x cubed plus 4x. Can the denominator be written as a product of factors?
Yes.
What would it be? X squared?
X squared plus 4.
Okay, and can x squared plus 4 be factored anymore? No, if it were x squared minus 4, yes, but x squared plus 4 can't be factored anymore. So here we would have something over x plus something over x squared plus 4. Degree 1 less than x would be constant. Okay, now this is truly a quadratic, right? So something 1 degree less than that would be x linear, okay? So that could include a bx, but that could also have a constant, plus c. Okay, so then what does that equal? That equals ax squared plus 4 plus bx plus c times x all over our common denominator, x times x squared plus 4. Did you catch it? Does that make sense? So now we split it apart and I get our general forms in the numerators, and we add them back together with those unknowns. So to add them back together, I got to multiply that first fraction by x squared over 4 over x squared over 4, x squared plus 4. And then I gotta multiply the second one by x over x. And that results in this numerator. Yeah.
Why did you write bx plus c?
Because the numerator is going to be 1 degree less than whatever the denominator is. It's a general form of a polynomial that's 1 degree less than that. That's what you need to do. So we've always had linear terms before down here. That's why we all had constants. We just had constants because that's 1 degree less than linear. Okay, so then this would be x squareds would be a plus b. What about x? Just c times x.
4a.
And just 4a. So our a plus b would be 0, because there's 0x squared in the numerator, right? 0x squared. C would be 0. There's 0x in the numerator, and then our 4a would be so C is 0. A is 5/2 from that last equation. So then B is negative 5/2 from the first equation. So this is piece of cake, 5/2 over x. Then this will be negative 5/2 x over x squared plus 4, which you all should know how to do. Recognize what you have and do it. Okay, so if you want to talk more about the trig integrals or tonight's homework, which will be this on homework, I'll be in my office at 8:30 in the morning tomorrow. And then we're going to push the test back from Wednesday to next Thursday, and then we will not have class next Friday. We will not have class. So our Thursday will be our exams, and then no class Friday next week. We will have class tomorrow. So next week we don't have class.
It's going to be right now. Okay, so what's the date? Pictures of this?
No, it's web work.
Oh, okay.
Do the web work. No, it won't be ready. You too.
Thanks.
Okay. See you next week.
So for the second one before this,
Yeah.
if we wanted to include every denominator, why wouldn't we include a second x minus 2 first? Right, why wouldn't we include it? Like why wouldn't you include 2 the first power or 1 in the second?
Well, so because we want to do this. That.
Right.
Which is just, what is that equal? That's just b plus c over x minus 2. It's just the constant. So that's redundant. It doesn't make sense to do that because it's just the same as that. Which is a constant. Okay. So the possible factors are x minus 3, x minus 2, but then x minus 2 squared would be a possible constant.
Yeah, that just
Possible factors that result in this kind of denominator. So you want all possible factors that result in that kind of denominator.
okay. So then, why would why would this?
The worst thing you can ask me
Because it's not cubed. Nothing's cubed here.
if I was thinking about what you do to add